There was no Earth, or any sun to warm it. Our solar system, with its glowing central star and varied planets and moons, is a relative newcomer to the cosmos, a mere 4.567 billion years old. A lot had to happen before our world could emerge from the void. The stage was set for our planet's birth much, much earlier, at the origin of all things, the Big Bang, about 13.7 billion years ago by the latest estimates. That moment of creation remains the most elusive, incomprehensible, defining event in the history of the universe. It was a singularity, a transformation from nothing to something that remains beyond the purview of modern science or the logic of mathematics. If you would search for signs of a creator God in the cosmos, the Big Bang is the place to start. In the beginning, all space and energy and matter came into existence from an unknowable void. Nothing, then something. The concept is beyond our ability to craft metaphors. Our universe did not suddenly appear where there was only vacuum before, for before the Big Bang there was no volume and no time. Our concept of nothing implies emptiness. Before the Big Bang, there was nothing to be empty in. Then, in an instant, there was not just something, but everything that would ever be all at once. Our universe assumed a volume smaller than an atom's nucleus. That ultra-compressed cosmos began as pure homogeneous energy, with no particles to spoil the perfect uniformity. Swiftly the universe expanded, though not into space or anything else outside it. There is no outside to our universe. Volume itself, still in the form of hot energy, emerged and grew. As existence expanded, it cooled. The first subatomic particles appeared a fraction of a second after the Big Bang. Electrons and quarks, the unseen essence of all the solids, liquids, and gases of our world, materialized from pure energy. Soon thereafter, still within the first fraction of the cosmic second, quarks combined in pairs and triplets to form larger particles, including the protons and neutrons that populate every atomic nucleus. Things were still ridiculously hot, and remained so for about 500,000 years, until the ongoing expansion eventually cooled the cosmos to a few thousand degrees, sufficiently cold for electrons to latch onto nuclei and form the first atoms. The overwhelming majority of those first atoms were hydrogen, more than 90% of all atoms, with a few percent helium and a trace of lithium thrown in. That mix of elements formed the first stars. First light. Gravity is the great engine of cosmic clumping. A hydrogen atom is a little thing, but take one atom and multiply it by 10 to the 60th power, that's a trillion hydrogen atoms, and they exert quite an impressive collective gravitational force on one another. Gravity pulls them inward to a common center, forming a star, a giant gas ball with epic pressures at the core. As an immense hydrogen cloud collapses, the star-forming process transforms the kinetic energy of moving atoms to the gravitational potential energy of their clustered state, which translates into heat once more. The same violent process that occurs when an asteroid impacts Earth, but with vastly more energy release. The core of the hydrogen sphere eventually reaches temperatures of millions of degrees and pressures of millions of atmospheres. Such temperatures and pressures trigger a new phenomenon called nuclear fusion reactions. Under these extreme conditions, the nuclei of two hydrogen atoms, each with one proton, collide with such force that the neutrons are transferred from one nucleus to another, making some hydrogen atoms more massive than others. After several such collisions, a helium nucleus with two protons forms. Surprisingly, the resulting helium is about 1% less massive than the original hydrogen atoms from which it formed. That lost mass converts directly to heat energy, just as it does in a hydrogen bomb, which promotes even more nuclear fusion reactions. The star ignites, bathing its surroundings with radiant energy while becoming even richer in helium at the expense of hydrogen. Large stars, many of them much bigger than our sun, eventually used up the prodigious supplies of hydrogen in their cores. But extreme interior pressure and heat continued to promote nuclear fusion. Two proton helium atoms in a stellar core fused to make carbon, the vital element of life with its 6 protons, even as new pulses of nuclear energy triggered hydrogen fusion in a spherical layer of atoms surrounding the core.